First, let's have a look at the equipment. So what do we have here? First of all, so this is the place where we will work. This, for example, now is a PCB holder. I'll show you that once we start with the soldering. We do have, a vacuum basically. So this guy here is basically there to suck in the fumes, which are so the fumes which are coming is there's flux, so there's a chemical within the solder, and if you heat that up, it will help you with the soldering, but it will also evaporate, and this stuff unfortunately is not very healthy, so we suck it away with this vacuum cleaner. Now on this desk, which is a little bit messy, but hey, we are going to do stuff here, so sometimes if you do stuff, this is a little bit messy. We do have a soldering station here with a soldering iron and also with a soldering vacuum pump. I'll show you that in a second. We have an ordinary soldering iron here, just like a basic one, and this guy over here. We will need this guy for SMD soldering, so but this is not much, this is not really the topic here. So we do have a heat gun, which we can use, for example, to shrink heat shrink tube. We do have a good light, and it also comes with a magnifying glass. I hope you can see that. So what else? We have some solder here, fine solder. We have thicker solder. We have some tweezers and so forth. Some duct tape. Okay, what else? Might be interesting. Maybe a knife could be helpful. This is also a solder pump, which we can use to desolder. And let's look, where is our flux? No flux so far. Okay, I'll search for that. Good. So your soldering station might look entirely different, but I think there are a few basics you should have. First of all, if it smells like chicken, you're holding it wrong. So this guy is getting really hot, right? And we're talking about temperatures of 400 degrees Celsius here. So obviously you need something below which is heat resistant, yeah, or is not prone to, you know, starting a fire. Please always make sure that you do have some kind of ventilation, or at least have the door or the window open, so that you do have some air circulation. When it comes to equipment, I mean, like, this is already quite sophisticated equipment here, which is pricey. But as an example, when I started soldering, I always had the impression that I'm very bad with soldering, because, you know, I had those kits you can buy from a shop to build a radio or something like that, and I never made that work. Okay, and I always felt like don't touch your face, don't touch it. I always felt that I cannot solder, I'm not good with that. But it turned out that this is only because of my poor equipment. So soldering is a lot about technique, yeah, and the quality of your equipment. So if you want to at some point get started with soldering on your own, don't go super fancy. I mean, like this Veller stuff, for example, this is top notch. This is more like going to the upper end. I would propose that you go somewhere in the middle, not too pricey, but also not too cheap. So how does a design process look like? On the physical side, I mean, like, of course, you first draw some schematics, you come up with an idea what you want to do. Maybe you do the math, you do the simulations, you do this up front, but at some point you want to build the physical circuitry for that. And I want to show you a little bit the usual design steps for that. In the beginning, in the very first approach, or in the very first implementation, you might want to use something like a breadboard. So what is a breadboard? In here you can see that you can plug in components into those holes here. And what you should know is that those power rails, they are connected horizontally from my point of view now. And those rows in here, they're interconnected vertically from my point of view. So what you can do if you have something like that, you can plug in components, you can plug in wires, and then connect all this stuff. Okay, so, and once this works, then we can, there are actually multiple things we can do now. For example, instead of a breadboard, we might also want to use, you can see that, well, it's almost transparent. You can use a prototyping PCB like that. So it's holes everywhere. And on the back side, you can see very, very tiny that for each hole there is a small copper pad. So you can still stick your components through. So usually the components are standardized to fit those holes, though you have to be careful because there are also components which do not fit into this standard. But anyhow, you can stick them through and you can solder them from the back so they do not get loose. And then you can use very tiny special wire to do that, to do the interconnection. And the interesting thing about that, or how this works, because you could now say like, well, if I have simply a piece of copper wire I use to interconnect the pins, then I have a short. But you don't. And do we have some wire? Whoops. Some wire. This is special wire because it is Lackdraht, Kupferlackdraht. So what does this mean? So this piece of wire is actually insulated in some paint, so this is what the name says, but it's basically some kind of insulation. And the interesting thing about this insulation is that as soon as you heat it up to a certain degree, so if you put it in liquid solder, for example, then the insulation dissolves, right? And so only at those points where you have the solder on the wire, only there it is conductive. Of course, this is prone to error, and I wouldn't, build a ventilator or some safety critical equipment with a technique like that. But for early prototyping, that's just perfect. Yeah, and you're very flexible with using that stuff. Okay, but you have to be careful when you do so, because if it's not hot enough, then the insulation will not dissolve, and then it's not conductive. Okay, and but you can see that that the wire sometimes does not really stick to the solder if you have a bad connection. So, but the idea here is heat it up good. You will see that the solder will connect to the wire where you want. Yeah, but you have to play a little bit around to find the right amount of time to do so. All right, good. So this is something we could do. This is a very early prototyping. Next thing we can do, for example, here at the university, is to mill a PCB. So this, for example, is a PCB we milled here at the university. I think it should be the exact same circuitry. Yeah, so this is the prototype. This is now the milled version of that. Milled because we do have a PCB with a layer of copper on it. And then we use something like a CNC machine, and there's a drill on top, and this drill will simply, cut the traces on the PCB. This is a rather simple PCB, so it will also drill the holes. This now, for example, is a more complex PCB. It's very, very nice for early prototyping. So here at our university, usually what we do is that before we send a PCB in bigger quantities into production, that we first will mill such a prototype PCB simply to check, for example, if our footprints are correct. If we made an error somewhere in our circuitry, you know, simply to have a quick and dirty prototype with which we quickly can test if our design is right. Because there are some drawbacks if you mill a PCB in-house. So, for example, the vias or the holes, they are usually not interconnected. So from one side to the other, it's simply, you know, let's see, where do we have a vias? I hope you can see that. I hope the camera is good enough. The vias is just a very tiny hole with a tiny pad, and it's not really connected to the other side. So there are several ways on how to conduct those holes, but usually this is really a pain to do this manually. There are PCB molds that can do this automatically. There are some techniques, but it's not really reliable. So what I usually do, and it's also a lot of work, is that I stick through a tiny wire and solder it from both sides. But this is really a pain. This is really a pain. Yeah, but it works. Sometimes you simply have to do that. Yeah, and once you're done with that and you know that your PCB is fine, then we can go in some PCB shop. You can do that on your own. There are several of those platforms and websites around, and you basically simply send them your Gerber file. So you export, for example, from Eagle or KiCad, you export your Gerber files and you upload that. They will say how many PCBs do you want, what color you want them to be, shipping will be that and that, and you will end up with a PCB, for example, like that. So this is what you get. One word about the ordering. I mean, like, if you order from China, for example, this is the price per PCB is lower, but usually they charge a lot of shipping. So we have some good experience also with German manufacturers, which are actually not that much, or they are not really more pricey, because first of all the shipping is obviously lower, and on the other side also the PCBs arrive within a week, most of the time. Yeah, and if you order from China, then it can easily take 6 weeks or more, and if they do have New Year or whatever, then it can take even longer. The advantage of such a PCB, or the difference, if we now compare, let's say, this PCB, this prototype PCB with the produced one, let's see, it should be like that, I guess. No, this way. Yeah. So also you can see here we had the problem that we could not produce the entire PCB because we do have physical limitations with our mill. The difference between those ports, it's quite interesting actually, because those boards are not that much different. If I would take away the paint from this one, the green stuff here, this would actually look almost the same, but this paint actually has a very specific purpose. It's called the solder stop mask, because the problem now with those milled PCBs is that you have copper all over the place. And if I now, for example, solder one single pin here, then it's very easy that or what can happen very easily is that the solder will connect to the outer copper here, and you do have a short, and it's messy to get this connection removed again. So what we have here is that only the pads or only the places where you want to have solder, you can see that also here for the SMD components, here it's a little bit more obvious, only they are exposed. So what you can do here is that you just bring in the solder and it will just go to the places where you want it to be. So, and this is a huge advantage. So how to use this soldering machine, this big soldering station. I mean, like if we take just a more simple soldering iron, then it's a bit more obvious. We can simply switch it on and off, and we do have a dial to adjust our temperature. What should be said is that for most soldering irons, you can replace the tip. So, for example, here we do have a very fine or comparable fine tip. So let's put that on again. But I mean, like, this depends now on the purpose and what you want to solder. Let's have a look at this. 1 second. So here we do have a selection of different soldering tips, and if you have, for example, a thick wire or something like that, then you can use one of those. If you want to go to the dentist, then we have guys like that. Or this is one of my favorite tips. You have a very fine tip like that. What you should notice, I hope that the zoom is all right. What you should notice or keep in mind if you choose your soldering tip, the more dense or the thicker your soldering tip is, the more heat it can bring into the solder. So if you have a very fine tip and you want to solder something quite massive, which can take a lot of heat and has a huge heat capacitance, then this will not really work, because the point where you want to have the heat, you will not bring it to the heat, because the heat will simply go away. Yeah. So always use the right tip for the job. Usually I take, as I said, I will take this fine tip here, because what I do here is basically through hole pin soldering, and SMD I usually do with the hot air machine. So for me, this is the main tip I'm using, but this really depends on what you want to do with that. Okay, now let's have a look at this nice machine here I just mentioned. Here we can simply switch it on and off and select a temperature. I prefer higher temperatures, which are usually around 350 to 400 degrees Celsius, but this depends on many things. So first of all, the solder you're using, the components you're soldering might not be that heat resistant. It depends on the material, on your base material of the PCB, how much heat it can take. So it has a lot of parameters, but or variables on which can influence the temperature you might want to use. I usually go for 350 to 400 degrees, simply because from my personal experience, this is just the temperature where it's hot enough to quickly solder stuff. So I do not have to have the soldering tip too long on a spot, because it's hot enough to do the job, but it's not so hot that it, for example, harms the PCB, the solder stop mask, and so forth. So this is my personal, yeah, it's not really a recommendation, but from my experience, this is a good temperature. Okay, let's switch this guy on, and here it's a little different. because we have two, how is this called? Handteile. I don't know, two things we can use. 1 and 2, and for each of those I can now individually select temperature. This is just an ordinary soldering iron, or yeah, it's basically just a soldering iron. And this guy is a little different because it has a small button, and if I press this, it's making noise. And this noise is coming because there is, on this tip, there is a small hole, and there is a tube going to this machine, and if I press the button, it will produce a vacuum and suck in air from the tip. And where this is extremely helpful is if you have, I will check if I can demonstrate that at some point, if you have excess solder somewhere on your PCB and you want to remove that, or what is really nasty, if you do have a hole and within the hole there is solder, then it's very hard to get that solder back out. And with this machine, what you can do is that you put some solder on that hole, place that tip above the hole, wait until everything is liquid, and then you simply suck the solder in, and then your hole is perfect again. I mean, like, it's basically the same thing as those vacuum or those manual things. Here you press the piston down, you place that, and you press a button, and it will do this. But it's sometimes, you know, I personally feel like I only have 2 hands, and it's nice to have it, but it's not really. Usually it's very difficult, and then the problem is that this tip usually is made out of some plastic, and it melts, and it's horrible. What else is around is this for desoldering. Not sure how I can open it, but what's in there is basically, I hope you can see in there, it's basically just a mesh of copper, and you place that on top of the pad, for example, where you want to remove the solder, and you heat it up, and it acts basically like a sponge, and will simply suck in all the solder which is around there. I can see if I can show that in a second. What else do we need? Okay, some Captain tape. I think we're ready to go. We're ready to go. All right, so this guy has heated up. I have this guy over here, and then this is the PCB I chose. I want to solder. We'll do some basic pin header soldering here. Maybe let's start with those over here, those 3 male pin okay, so put that in my stand here, the camera. I hope that you still can see it. And then I will have it like that. No, the other way around. Somehow like that. Okay. So what we can see now, here we have, maybe that's better, light. So the light is not as good as I thought it would be. So what do we want to solder? So those are the 3 holes, and on that other side, this is where we want to have our connectors. Okay, good. So let's start. First of all, we need to get the pins which we want to solder. I don't have them here, so 1 second. Okay, so this is how they look like. They usually come like this. They can be longer, shorter, and they do not have too many parameters. The distance between those pins is standardized, but there are different standards around. So you always want to make sure that the pin spacing is does fit, right? So for example here we need 3 of those guys, and what I can do now is that I simply snap that off like that. If you want to snap off just an individual one and you do not want to break your fingernails, then you might simply want to use one of those guys. So the problem now is the following. I mean, like, this is where this should go, all right? And gravity just pulls it in the location we want to have. But if I turn this now around, whoops, gravity will do its thing. There are now several ways on how to camera adjustment. There are now several techniques on how to get this done. What I usually do if I'm at home and I also do not have this stand here, that I will simply, you know, carefully do not burn your fingers, because the metal in here is heat conductive. Simply hold it like that with the finger, go on the back, solder the center pin, then turn it around, check if the alignment is right, and if I know that it is right, then I solder the other pins. Yeah, but this is like, you have to be extremely careful doing that, and I really do not recommend this technique, especially not if you do not have that much experience with soldering yet. There are now other techniques on how to do that. One technique is to use so-called Captain tape. So this is Captain tape. It looks a lot like high-tech and science and space, because it is. This is the material which is used, you know, to wrap wires and so forth, because this special kind of plastic is very heat resistant. So what you can do with this stuff, let's take a little bit. Let's take a little bit. It's just like, you know, any other tape, but it's just, you know, a bit yellow. And then you can use this to put it somehow, you know, okay, this was not enough, but you would now use this tape simply to tape the component you want to have fixated on your PCB, so that you can solder it from the other side. This thing here has a very handy tool or feature, which is this spongy arm thingy. Because it is connected to the left hand side here, it will rotate with the whole PCB. And what I can do now is that I would simply turn it around. Aha. And it's still there. Okay, now I only need to check how I can film this. I hope that it is in focus. Now the interesting thing starts, the soldering itself. So let's solder some pins. There again, like all the time, there are different techniques on how to do so. For example, what you might want to do, or what you maybe should have done up front, is to put some flux on the pads. There are different types of flux around. There is some flux paste, for example, which is commonly available, but and I used to use that stuff for quite some time. But yeah, well, once you know that there are, for example, some pens available. So what does it say? Mini fluxer. Yeah, it's just a pen, and you could now, you know, just use this pen to bring some flux on on the pads. But for the solder I'm using, which has flux included within the solder, I usually do not use extra flux. So I just use the flux which is on the which is in the solder itself. One word about this here. So in order to clean the tip before you use it, you can use those metal sponges. So it's basically the same like if you have a pot at home and something burned inside and you want to clean it. That's the exact same stuff. Sometimes you also have wet sponges which you can use to clean your tip. How often should you clean your tip? Because I have seen students doing this basically all the time. Yeah, and then at some point there was no sponge left. Why do we need that stuff in general? If you look at the tip now, you can see that it is clean because we can see the metal. But obviously we work with rather high temperatures, and they are, for example, I don't know what it is. It might be oxide, I guess, remains of the flux. If you accidentally melt some plastic, then the plastic might be stuck on the tip and so forth. Okay, but now let's do the soldering. For this I will not switch on the vacuum because otherwise you cannot hear me anymore. But as I said, please, if you do soldering, then always remember to have the vacuum on. Just very few words about the actual process. What you should note is that this stuff here, especially the connection between the copper and the base material, as well as the solder mask, they are heat resistive to a certain degree, and they are not strong enough to withstand the 376 degrees I right now have on that tip. So what this means is that if I do the soldering, that I have to make sure that I'm long enough on that pad to get the job done, but not so long that the PCB actually gets damaged. So what does this mean? Too long? I do not have any numbers. This is just personal experience and a lot of broken boards. But I would say do not exceed something like 10 seconds. Also, what you should notice, if you go step by step, let's say you start with that and you go forth, then of course you create a local hotspot here, and then the next pin already has some heat if you move on, and you should take that into consideration, especially if you're soldering integrated circuits with a lot of pins. Okay, let's see. How I usually do it is that I have the soldering tip somewhere in the back, and then I bring in the solder from this side. Wait a little bit, and that's it. Okay, it's now really difficult for me to do the soldering because I do have the camera in between, and this is not I'm not really used to this angle. But basically how it works is that the surface tension is your friend, okay? Before I continue, let me check if this now is correct. So we can look from this side if there's a gap. No, there is no gap. And I can also look from this side if this is perpendicular. Yes, this looks all right. This is okay. No need to be perfect in this case, but also shouldn't be too ugly. Stupid camera. All right, so let's continue. So what is important is that surface tension is your friend, okay? So I hope that you can see this. If I bring in the solder, it will first stick to the top of the pin, but the very moment everything is
hot enough for the solder to stay liquid, then the surface tension will make sure that the whole liquid is sucked to the entire pad. And this is the point where the flux, which is in the solder, becomes important, because it will make sure that the solder can flow onto the metal by etching away, for example, oxide, and also breaking the surface tension of the solder. What you now have seen is that this took a little longer. Yeah, so first we had a small ball of solder on top of the pin, and then I had to heat it up a little more until it eventually, you know, got sucked onto the pad. What is the reason for that? This is the ground pad, and the ground pad now is connected to all the copper which is around here. So if I heat that up, then I have a huge heat sink which will distribute the heat, yeah, so that the heat does not stay where I want it to have. And for this particular reason, if you do the design, then wait a second. If you do the design and you have something like a filled area or an area in KiCad, let's say, then you can choose if you want to have so-called thermal pads. And what this thermal pad will do is that, let's see, with our PCB here, if we do have a thermal pad somewhere, yes. For example, those, let's say, those are thermal pads. I hope you can see that, which means, because if you do have, for example, let's say I want to have a connection to ground, you could basically simply drill a hole and solder it from the other side. But let's imagine now you have something like a hole here and you want to solder it, then the heat will go into the copper and it will not stay where you want it to have. So instead you have those this outline basically around the pad, which will make sure that the heat can build up at this particular spot. Have noticed, this is a pain and it really took some time to do this by hand, but two things. So first of all, what I did is that instead of individually placing every single
pin header onto the PCB and soldering that individually. What I did is that I just took the same PCB and made this kind of sandwich thingy here, because this will now simply hold everything in place. And what I will do now is that I start with the components which are very low, and then step by step, the bigger the components get, the higher the components get. I'll simply stack that up. You have to sometimes you have to be creative to come up with ideas on how to get a job done, especially if you do this manually. There is no rule on how to do that. But I just also briefly want to explain you how this usually is done industrial, or if you do this on a bigger scale. For through-hole components like pin headers, so through-hole simply means the component goes through hole. And if we look at it like that, you can see that the pins, they are visible on the backside. And I'll try to find a video for that, or a link to that, or include it into this video. But how this works is that there is a belt, and the PCB with the components is moving like that. And then there is a wave of liquid solder. And then it will simply go over this wave, and then all the wires which go through the holes are soldered from the backside. So on an industrial scale, this is just a matter of seconds. If you do this manual, then especially if you have many pins like with this PCB, it really takes some time. And if you do not come up with good ideas, or sometimes it's not possible to come up with good ideas because there's no handy solution, then this really can take some time, and it can be really frustrating. So I just gathered the components. I have to bring on that PCB, and just to give you an idea, so we have this potentiometer which has to go somewhere like here. Like the pins are a little bit bent, so I first have to fix that, but you can see that is this is quite high. So from the height, We have some buttons. The nice thing about those buttons is that, I mean, like if you have, let's say this guy, why are all the pins bent? Yeah. Usually, I mean, like the pins are bent now, so it is a little bit stuck. But usually, for example, with the pins, you turn that stuff around and then it falls. It doesn't really stick, you know, so it falls out. What's nice about, for example, some components, the pins are designed in such a way that once you have put that through, then it cannot fall out. But there is one more nasty thing to do, which is those are male pin headers, those are female pin headers, and we have the same issue now with the female pin headers like we have with the male pin headers, so that if we turn that around, okay, then it falls out and we cannot really solder it, and we have to make sure that it's perfectly aligned. Otherwise, the components which you would try to put in from the top would not fit. So what I want to try here is, never done that like that, is that I will insert the female pin headers everywhere where it's needed. Then again, I will do my sandwich, and then in order to make sure that this is perfectly aligned, I want to stick in some pins from the top, and then I can solder from the back. Of course, I now have to check, or I have to think about with which components I start, because I want to use the sandwich approach. So for example, now I can see that the buttons are lower, I hope so at least, than the female pin headers. So I'm thinking about maybe I start with the buttons here, simply because I like soldering buttons, I don't know why. So maybe I start with that, and after that I will come with the female pin headers, solder everything I can, and I will stop the time lapse whenever I think I do something interesting. Just a quick notice here, if I do have a component which has a lot of pins, what I usually do, and especially if it's upside down like it is right now, that I first solder, for example, that pin here, and then the diagonal, I don't know how to pronounce that, the other pin on the other side, solder that one, so that it's fixated. Because if I only solder one side, then still gravity could pull on that, and then it would not be perfectly aligned. So I always try to make sure that I have I first solder the pin so that it's physically fixed, and once this is done, I can solder the other pins. Okay, so I have a small problem now, which is that if I have those through-hole components and there's no spacing, and if I put them now on the surface, then they might get pushed out. So what I will do now is that I place some spacers through here like that, simply to make sure that if I have the stuff, you know, that simply it's not getting pushed out. So, but I think they might even be a little bit, they might not be high enough. So I just check if I have longer ones and make that happen. have seen, I used some Kapton tape to fix the components, and what I want to do now is, I already did it with that guy here, I have one pin soldered, and I will also do this for the others where it makes sense. So for example, for this socket down here, just take a pin which is maybe easy to solder, so no ground or supply pin. Can do the same thing here with that connector. So here the Kapton becomes handy because you can see I can just place the soldering tip right on the Kapton. It will, you know, deform a little bit, but it will not melt because it's really temperature resistant. What I do next is I use my finger, so again be very careful, and giving it a little bit some force from the other side. I'm just making sure that it's really in place, okay? So I've done this once for one side. I will now do it for the other side, okay? Once the solder is on, so what I do now is that I first bring in some solder, make sure that I do have a good solder here. Then in the next step, I heat that up again to bring it into position. The reason why I do so simply is if you would try to do everything in one step, then this might simply take some time and you might burn your fingers, right? So that's the reason why I'm doing it like that. And let's continue with all the other stuff. And also what I found is I forgot to place a pin header here, and it's very likely that I also forgot more stuff. So yeah, but so far I'm happy with that so far. So what happened, or not really what happened, but what's the issue now? This is different now because here we do have a connector, a barrel connector, and the pins here are way bigger than those small pin header pins. So I will demonstrate that a little bit. I hope you can see anything, but I like, let's change the camera perspective a little bit so that the video also is maybe not getting too boring. Maybe like that. Oops. This is tricky. Alright, so the problem is those guys are obviously way bigger than those small pins. And what I want to show you here a little bit is how we can solder stuff like that. So first of all, this might not be the perfect tip to do this. Yeah, so actually it's such a fine tip, and this will simply take some time to bring in the heat, but I also do not want to change this right now because yeah, it simply takes a little bit more time. So what I will do now is I will bring some solder. And you can see already surface tension. Alright, and then I move this a little bit, and now you can see as surface tension is doing its job, and I get a beautiful soldering here. Let's try this again. First it's a bubble, but already here surface tension. Okay, now that I have the surface tension, I can bring in more solder and just simply decide how much solder I want to have here. So, small blob. Wait until I have surface tension and then continue. I actually do not even need to look at it. You can see it from the back side here. And maybe turn that a little bit. We'll do that again. Wait a little bit, surface tension. Wait until everything's liquefied, and beauty. have some interesting components to go. So for example, we have a couple of diodes and we will have some resistors, and I hate those, and I will show you why, but I mean, like, you can handle it. The problem is that if we have a component like that, that we need to bend the legs in order to make this component fit. This diode is now way smaller than the footprint I used. This is simply because I had no idea what kind of diode I want to put in here, but I think I'll take this, or yeah, I think that should be fine. I think that should be okay. So the problem is, if I now would bend the legs by hand, then quite often this is a mess and it looks ugly and it does not really fit. So what I do is that I will use the tweezers and then grab it just at that point where I want to have the bend, and then let me see, like this should be correct, and then I will simply, do it like that, and then you have a beautiful bend here, and I can just continue to do it like that, and then I know that this is just nice. I can put it in, and yeah, the usual stuff. Okay, quick question. What is a difference between a resistor and, let's say, a diode? Yes. I hope you got the right answer. Diodes do have a polarity, right? So a resistor, for example, doesn't have that, but a diode does have a polarity. And what we can see now on the PCB is that, for example, here for diodes, we do have a marking here. We have a marking on the component itself. I hope you can see this. There's also a small marking on that. And an LED is a light emitting diode. So it's also a diode, and thus it has also a polarity. We have several ways on how to identify the polarity on an LED. For example, on one of those we have legs which have a different length. I'm honest, I have to look it up. I'm forgetting it all the time, which one is which, but we have legs which have a different size. We cannot solely rely on that, because if somebody just was cutting one leg, then this is not reliable anymore. You can have a look at the inside of the diode. If it is transparent enough, then you can see the inner shape and you can look up which leg is doing what. And there is another marking on it, and which is on the housing, because on the housing there is one side is a little bit flat and the other side, or the rest of the housing, is simply round. And if we carefully look at the printing on the silk screen of the PCB, we can see that on one side of this guy there is this marking for the flat surface, so this goes in like that. So from that I know that the LED has to go in this way. Noticed that it took some time to solder this component, and the reason for that is that the holes of the footprint do not really match the physical pins. So if you want to make sure that a component is perfectly aligned, then you always have to make sure that the holes of the footprint you're using do also fit the pins, because otherwise if this is too loose, then obviously it can move and you will have problems aligning that. What is next is that I will perform a first smoke test. So I will bring some power to the board, and first of all I want to check if anything is burning, which it is hopefully not.
I want to see if this LED is working, if it is igniting, because it should be simply be on if power is on, and then I will simply use a jumper wire and will try to make all LEDs ignite at least once, so simply to check if all the LEDs are, if the polarity of all LEDs is correct. Talking about tools, I think this is a must-have, because with this tool you can remove insulation. You know, now a third arm would be helpful. I'll just record that from the other side. Because what you can do with this tool is that you simply insert a wire and ta-da! Beautifully removed insulation. Please do not use your teeth or something, because if you do so for some time, then your dentist will be very happy to help you. What I will do now is that I will cover those tips of the wire in some copper, because I want to put them into this screw terminal here. And if you have loose wire, it depends on the terminal. I think this terminal might even work with, I'm not too sure, because I'm afraid if I put solder on it, then it might not fit anymore. Let's try. Let's try. But usually what you do is that you cover the tips in solder to make sure that the fine wires don't go anywhere. But in this case now, let's see, does this fit? Not really. In this case now, I'm simply afraid that they are, the wire is too big. The wire is too big. Damn. Okay, I need to come up with another solution. Okay, so I found those old wires. They are not great. They are not bad, but they should do the trick. So let's plug in the power supply. And what I will do now is that I will heavily limit the current. So as soon as the board is connected, I will slowly ramp up the voltage. And if there for some reason is a short, then the supply will limit the current. So I have a chance to search for it or check, for example, which component is getting warm. If I would not have a current limitation and I would simply switch it on, then it, you know, will simply, the error might evaporate, and this is not what we want, because it might happen that the PCB gets burned or stuff. So I'll plug that in. I need a third hand, anyhow. Okay, so we're live, and now I'm slowly ramping up the voltage. So 1 volt, nothing happened so far. 2 volt, 3 volt, 4 volt, nothing. 5 volt. Oh, LED is not on. Okay, so this is not working. Alright, now, because there is this external power thingy, which I need to short, otherwise I do not have the supply, so I will need to get a jumper. Now we have a jumper. I hope you can see it. So the idea here is that you can, on this board, you can say if you want to have external power or not, or if you want to power the board simply from the microcontrollers. So again, so 1 volt, 2 volt. Oh, there was something. I saw something. Yeah, it made something. Yes. It's blinking. It's blinking because it's below the specified voltage. 6 volt. 8 volt. No real current. Okay. 190. Okay. Awesome. All right. So let's simply, whoops. This should be positive. And now we can try. Blink, 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 and so forth. I will test all of them.
one thing I want to show you here is yeah, those nasty dual inline packages. They're very nice, I like them because they're easy to solder, but on the other hand the problem is for some reason they always have the legs, they spread wider to the side than the holes. So what you have to do is to extremely carefully bend those legs inwards, and usually I do it like that I use like quite some surface of my fingers to do so, and then all the time try to fit that in. And what I want to show you here is also for those dip packages. There is a marking on the silk screen, there is a marking on the socket, so I place the socket in such a way that it aligns with the marking on the PCB. And here on top there is just another marking, so from which I know that I have to place it like that. So this will take some time to bend that. What I want to say here is that if you bend that, try to use tweezers, or I've done that so many times that I'm quite good to do that with my fingers, but don't bring too much pressure on a single pin because it will bend very easily. So what I do instead is that I try to bend several pins at once and very carefully. Okay, so first it's a light. Yay! So the board is almost done. There's no real short or anything. What I will do next is that I'll get the microcontrollers, which should be, or which I want to have on this board, two PSOC 5 LP prototyping kits. I have to solder the resistors. I have to, I can show you this kind of thing. We do have those spacing components, or those spaces here. You basically have some screws. You have those guys, they have a hole on one side, on the other side they have a screw. They come in different length and different colors. This is now, what is it, I don't know, M3, I don't know. Might be different. I'm not an expert when it comes to that. I'm not a mechanical engineer, I'm an electrical engineer. But those are a little bit smaller, the ones which should go there, because we want to have at some point the OLED screen here, and we want to have some physical, you know, attachment here, so that it's simply fixed here. Well, and after this is done, this board is also done. Thank you a lot for watching. I hope you enjoyed the process. And I hope that at some point we can meet again at the university, and I really would like to do that stuff with you. So far, thanks for watching again. Stay healthy, wash your hands, and goodbye.
will you?
No, sir. I'm staying right here.